Hey everyone, in this video we're going to take a very careful and considered look at the idea of how information makes it into the different tables in the confines of EIGRP. Now, thus far, we've talked about the fact that in the environment that we're running here, we have load sharing. Now, we've been playing around with some stuff. We may have to go in and tweak some things out and take some commands off. But the main goal here is to recognize, first and foremost, that we're going to do some type of load sharing for the majority of the interfaces that we're going to be originating from R1 in our topology. Now, I'm going to take myself out of the equation, and I'm going to verify that. And I'm going to verify that on R22. So from the data center, from the offsite data center, what I want to do is I want to see if I have reachability to prefixes that are being originated on R1. Now, very quickly, let's just cut over to R1 and see what prefixes we have there. Show IP interface brief, E assigned, and we can see we have quite a few of these. One of them is administratively down. Let's go ahead and fix that while we're here. Config T, interface LO 116, no shut. And let's take a look and see what's happening on R2. So if I go, R22. So if I go over to the data center device, in fact, just to make my life easier, I'm going to drag R22 over here since we're going to be doing so much verification on it. Show IP route, EIGRP. And let's see what we've got going on here. Well, to 11.0.0, 1.0, 2.0, 3.0, 4.0. We're not load sharing. Notice what we're doing instead is we're actually sending, oh, hold on. Yes, we are. I apologize. We're not doing it for all of them, though. Yes, we are. All right, so all the commands have been removed. Fastest way for us to verify this is to use the trace route. So I'll trace route to 11.11.0.11, and what we can see is indeed we are load sharing. Our data is going both to R2 and R3. From R2, it's going down to Cat1 all the way to R1. From R3, it's going to Cat2 all the way to R1 until it's reaching our interface of choice. And for the purposes of our testing, we're using 11.11.0.0/24, where that's .11 on R1. Now, this is going to be a pretty straightforward explanation because what I want to do is I just want to entertain how information gets placed where. Now first, we have three tables. We have three tables in the confines of EIGRP. We have the adjacency table, we have the topology table, and we have the routing table, or the RIB. Now, what I want to do is I want to explore each of these in turn. We're going to start first with the adjacency table. How do I know what devices I have that I'm adjacent to? Well, simply enough, all I do is on the devices I type show IP EIGRP neighbors. And it's going to give me a detailed list of the devices that I have adjacencies with. This is my adjacency table. Notice it's giving me an IP address that is being used as the ID of my neighbor. So I know on R22, the data center router, I have an EIGRP adjacency to both R2 and R3. And I also know, and I'll take myself out, I also know that based on this output right here, that my connections are fine because my queue counts are at 0. Now remember, ones, anything other than 0 in that particular slot means we have problems in our infrastructure. And we'll entertain that, especially when we start exploring this idea of DMVPN and how it can affect our EIGRP configurations. Now, looking at what we've got right now, the other table that I want to highlight is this idea of the topology table. Now, the topology table is very important because the topology table gives me a detailed listing of all the prefixes that I have to reach a particular destination, provided certain situations or conditions have been met. And that's what we're going to explore in the next couple of videos. We're going to take a look at these conditions that must be satisfied in order for prefixes to be incorporated into the routing table from the topology table. So think of it this way. The topology table is a list of candidates that have satisfied an EIGRP principle called the feasibility condition. And of those prefixes, we know that we have a loop-free infrastructure such that if we lose our primary route, the route that has been placed in our routing table, something referred to as a successor route, what's going to end up happening is we can use any of these prefixes to replace the successor, and that's why we refer to these as being feasible successors. So it's feasible to use these because they're loop-free in the event that we lose our successor route, which is going to be the best route, the route with the lowest metric. Now let's look and see what we have going on here. How do I see the topology table? Well, I type show IP EIGRP topology, and I'm going to be able to specify a given prefix. I can do all links. I can even look for details associated with my links. So what I'm going to do first of all is just going to hit enter, and you're going to see we have a lot of information. Now what I want to do is I want to single out the 11.11.0.0/24 prefix that we were using for testing. And what I want you to see here is it's going to give us quite a bit of information that we don't have in the regular form of the command. Now when we look at this, what do we see first of all? We see the fact that both of these prefixes are going to be treated equivalent in routing because they have the same metric. Let me take myself out and let's look at that. My composite metric for this particular prefix is 2195744, and it's 2195744 for the second way to get to it. Notice this is through serial 20. This one is through serial 21. So actually this is going to be transiting R2 to reach R1. This one is going to be transiting R3 to reach R1. And by virtue of the fact that these values match, we know that these are going to be the prefixes that are placed in my routing table. Well, how do I observe that? Well, there's another command. We've used it several times up to this point to verify the contents of our routing table, and that command is going to be show IP route. So what I'll do is I'm going to come up here and say show IP route EIGRP. Actually, no, what I'll do is I'll show IP route 11.11.0.0.255.255.255.0, and what we're going to see is the same information that we saw on the topology table. Now what we're also going to note here is that each of these are going to be used for routing. Now I can see this in a simplified form just by typing show IP route EIGRP, which is what I was going to do initially. And if I look right here, I'm going to see to reach this destination, I'm going to load share via this link and that link, which we've already illustrated using our trace route. Now what we need to understand here is the fact that these prefixes have been placed inside the routing table by virtue of the fact that their metrics match. They're both going to be 2,195,744. Now remember, this is going to be a combination of factors, and we also have to take into account whether we're using classical EIGRP or we're using named mode EIGRP. Remember, classical EIGRP is going to basically, when it's all said and done, because K1 and K3 are on by default, what's going to happen is we're going to use the lowest bandwidth in our infrastructure in kilobits, and we're also going to use the total of the sum of all the delays across our link. Now, in the confines of named mode, remember, we illustrated the point that we have latency and we have throughput. Throughput being the K1 in the idea of named mode, and latency being the equivalent of the delay. But keep in mind, delay is measured in picoseconds, not microseconds. Classical uses microseconds, and the idea of named uses picoseconds. So what we're going to be doing here is we need to understand, first of all, how we can manipulate this process, because what I want to illustrate here is what we see is the idea of equal cost load sharing. What I want to do is I want to entertain the possibility that we can still do load sharing. Let me change pins here. Sorry about that. We can still do load sharing. We can load balance in circumstances where our metrics are not equal. But there is still a situation that we have to take into account, because we can only load balance against unequal paths if each of those paths are in that topology table. So you can see the significance and the importance of the topology table very quickly, because if these values, this value, let's see, no, it's going to be this value right here and this value right here, if they were not equal, I still have the capability of being able to send traffic in a metered process whereby I would favor one link over the other based on what's called the share count. Now, what we've seen right now is exactly what goes into creating equal cost multipathing, but the question is, how do I do load sharing across unequal paths? And that's what we're going to entertain. Right now, all this was the introductory to the process that goes into selecting prefixes. So what happens is we have our neighbor adjacencies, which are a list of all of our neighbors. We exchange prefixes and updates with our neighbors, and through that exchange, we construct the topology table. We'll talk about the feasibility condition very shortly, and provided we have that satisfaction of the feasibility condition, we're going to place those prefixes inside the topology table. Other prefixes that we have in the topology table, we run the diffusing update algorithm against those, and what we do is we decide which ones we're going to place in our routing table. The diffusing update algorithm, first of all, determines whether or not the feasibility condition has been set, and it also allows us to calculate the metric. The lowest metric is going to be placed in the routing table. If we have matching metrics, we're going to do load balancing or load sharing by default. So with that being illustrated, let's move into what's involved in manipulating this process, and we'll do that process in the next video. I'll see you there.